Now, how to present your statistical results in proper form and how to read statistical results coming from different people. Again, disclaimer, this is not mathematical statistics class. In this short video, I'm following mainly Introduction to Error Analysis by John Taylor, which is fantastic, very beautiful book, showing a beautiful error on its face. So, significant figures or significant digits concept, you should be familiar with that from general chemistry class. So we say that 23 is a two-digit number, there are two significant digits, and the same is 0.0023. Zeros before do not count as significant digits. Zeros after the number can count or cannot, depends on circumstances. There is approximate correspondence between significant figures and relative uncertainties. If you have one-digit number, relative uncertainty is somewhere between 0.1 and 1. On average, it's 0.5. It's very large relative uncertainty. Two-digit numbers have uncertainties from 1% to 10%. On average, it's 5%, or in fractions 0.01 to 0.1. Three-digit numbers 0.01 to 0.01 here. On average 0.5%, and so on. We can continue that, but relying on significant figures only is very bad practice, to say it. So how we write uncertainties? We always should write uncertainties, so how we do that? There is one simple rule. Experimental uncertainties should almost always be rounded to one significant figure. So uncertainty is one-digit number. Possible exceptions. You can use two-digit numbers for numbers between 10 and 15. Some people say between 10 and 19, so anything less than 20. Another exception is that larger numbers are used for very accurate work with more than 100 measurements. We never do such work in our laboratory, so we are never using this approach. So how does it work? Say you have number 9.82 meters per square second. Actually, it's gravity acceleration at Earth's surface, and there is an error provided as 5-digit number. It's coming from calculator, but it doesn't make sense. You do not know error with such precision. You should round it to one-digit number, which will be simply 2. So you're writing 982 same way, plus minus 0.02 meters per second. Now, if uncertainty is 0.1138, you retain 11. But if it's 1838, you write 002. Well, some people will write 18. If they are using this rule, I never use that. Now, how we are writing the answer itself? The last significant figure of any stated answer should be of the same order of magnitude in the same decimal position as the uncertainty. So we have uncertainty 0.325. We round it to 0.3. That means our number 51.418 should be rounded to 51.4, the same digit as in your uncertainty. Same way, 51.8 plus minus 30 meters per second is nonsense. The correct answer should be 50 plus minus 30. This 0 is not significant digit. It's much easier to use scientific notation for that. So it will be 6.05 10 power 3. So for example, the proper answer will be 161 plus minus 0.005 by 1019. If uncertainty is larger, it can be 162 plus minus 0.11. If uncertainty is even larger, we are removing next digit, so you'll have 1.6 plus minus 0.2. Same. The last issue is outliers. Let's consider such an example. We have 4 titrations: 40.35 mils, 40.40 mils, 40.50 mils, and then 30.50. What is that? Most possible this is a typo, but you should resist temptation to correct the typo if you do not know for sure. If something is written in your notebook or typed in your file, it should never be replaced. It should be corrected by some mathematical apparatus, some algorithm. Now, if you'll take all 4 numbers into account, average will be 37.9, far away from average of first 3, which is 40.42. They are close to each other. Now, this is absolutely wrong. It cannot be tolerated. It cannot be left this way. Now, still removing outliers is necessary, but very questionable process. When you stop just removing outliers and start cheating. So we need some algorithms, and some of them are written in your book. Usually we have a good explanation why this is true, but in practice it should be clearly written in your notebook. You should never delete this number. You should leave it. You should exclude it from all calculations, but you must write the explanation of doing that. Now there is a very straightforward solution of the problem. You are using different estimate of your value instead of average. Average is very sensitive to outliers, but we have robust estimates that are not sensitive. An example of that is median. If I am using median instead of mean, my median of all these 4 numbers is 40.38, which is very close to 40.4, practically the same. So if I remove this measurement, artificially it's become 40.40. So the change, the price I am paying by removal, is practically non-existent. This estimate, median, is very stable, and we say it's robust. On practice, If you have small number of measurements, 3 to 5, median often gives better estimate than mean. And for many measurements, we are using small numbers. Actually, we seldom use larger than 5. Now, for large numbers, mathematicians have many sophisticated, robust estimates to replace the mean. For using them, you need to read mathematical statistics, or better, ask for help for specialists in statistical mathematics.